All right, welcome. Please take a look at, if hopefully you grab this sheet called Introduction to Forces. It's on that stool. It's also linked via Canvas as a PDF that you can mark up. We are starting your 2D motion tests are graded. They were posted Monday or Tuesday already on Canvas. So we'll take a peek at your scores. If you weren't here for it, we should take care of that really soon so we can get that done. We are starting our next unit. Sorry, on forces, and I'm going to be upfront with you that forces is probably one of the most difficult units of the year. And the reason it's one of the most difficult units is because up till now, when we did our problems, we made a list of variables based on problem types and from the problem. Based upon what we knew, we said, oh, equation number 3, you plug in numbers, and then we solve, and then we're done. That's not the case with forces, and that's our next unit is forces. Forces gets to be a little bit more abstract from the standpoint of we have to build an equation based upon the situation we have. We use the same equation, Newton's second law, over and over and over again, but it looks slightly different based upon the information that's given. So because of that, students tend to struggle a little bit more. So I created this sheet to try to kind of help you introduce some terms. In the past, I've written all this on the board and hoped that people copied it down. I omitted a few things that I've added, so my apologies on that, but it's not too big of things that I missed. So forces is the unit. So we should probably start with what the heck is a force. A force is a push or a pull. It's a push or a pull on an object. Some people get into this whole, is it a contact force or a non-contact force? It's a force. I don't really care. A contact force would be like, if you were to push me, now notice how you're pushing me, because if I push you, I'd probably get fired. So you pushed me, so because you pushed me, we are in contact with one another. That's a contact force. However, if I take this and I drop it, gravity was pulling on the object, but it's not in contact with it. So sometimes they classify them like that. I sometimes slip and call it the force, but it's not the force, it's a force, right? Because the force is Star Wars, and I forgot, and I feel really bad. It actually ruined my day when I realized I forgot. I always, for years now, on the first day of the forces unit and on testing day, I would always wear a Star Wars shirt that says may the force be with you, and I forgot. I apologize, everyone. I'll try to make it up somehow. I don't know how I could ever make that up to you, but I will try throughout the year to make that up to you. So if I slip and say the force, not the force, not the metachlorians and all that stuff, Jedi powers, a force. It's a push or pull on an object. Okay? It is a vector. So remember, vector is committing crime with both direction and magnitude. Thank you. Oh, yeah. Okay? So we need directions, but this time instead of using positive and negative signs, we tend to use arrows. And we draw these things called free body diagrams. And the free body diagrams are pictures that have arrows coming out, and the direction of the arrowheads tell us which way it's going. When we go through and we assign pluses and minuses based upon those arrows, and then we can kind of backtrack and say, oh, well, because it calculated to be a negative, then that is also a direction of left versus right. But it is a vector, so we need to include a direction. When we talk about forces, all forces are measured in newtons, or this should have been units of. All forces are measured in newtons after Sir Isaac Newton. And the abbreviation that we use is just a capital N. So if you ever see an N next to some number, 15N, it's a force. It's not as helpful as like meters per second squared is as a unit, because then that's an acceleration. And N tells us it's a force, but all forces are measured in newtons. So here is a list of forces that we will use throughout, and I'll show you why. I forgot one. Sorry, that's one of the things you gotta add. But in the parentheses are the abbreviations that we're gonna use, and it's a subscript. So it's an F subscript G, it's an F subscript N, it's an F subscript F. The big F means force, it's a force of some shape and form. The subscript tells us what force it is. So F of G, F of N, going across the top, F of F for force of friction. Then going to the next row, I'll talk about some of those other things I've written under. Applied force is FAPP or AP. Tension is F of T. Air resistance, we do not do a lot with air resistance, but it's F of air, F air. And the one you should add, because I forgot, is the force of a spring is Fs. We don't do a whole lot with air resistance. We do a little bit, like today and tomorrow, we'll do tomorrow's homework, we'll talk a little bit about air resistance as like a quantity. But we still kind of live in this simplified like reality of like, oh, just ignore air resistance. It's not really that big a deal. Well, it is really a big deal. But we just kind of, we don't do a lot with it. And the reason we don't do a lot with it is it's a very great thing. So in order for us to calculate it, you actually have to do calculus. And the idea is if you're driving in your car at like 5 miles per hour, is there air resistance? Yeah, there's some, right? But when you're going 55 miles per hour, is there air resistance? Yeah, there's more. So there's more air resistance as your speed increases. In order to do a calculation like that, you gotta do some calculus. So we are gonna calculate these numbers. So force of gravity, I have AKA weight. So if I ever say something weighs 10 newtons, I'm telling you the force of gravity. If I say what is the weight, I'm asking you to solve for the force of gravity. For normal force, a normal force exists anytime an object is sitting on a surface. So like for example, my water bottle is sitting on the surface of this desk. My desk is sitting on the surface of the floor. You are sitting on your seat of your desk. So there's a normal force. And this stool, even if I drag the stool, it's still sitting on the surface, so therefore there's a normal force. The normal force always is perpendicular to the surface, and because we don't do trig functions in here, it's going to be straight up in the air. But technically, if we did an incline, then it would adjust the angle with it, and it's always perpendicular to the surface, but because our angle is 0, it's always 90 degrees. Force of friction always opposes motion. It's always in the opposite direction. So if an object is moving that way, the force of friction is that way. If an object is moving up, the force of friction is down. Always opposes motion. It's always in the opposite. Now the reason I highlighted those three, and whether you choose to denote it or not, I don't really care. Of these 7 forces, 3 of them have their own special equation that will kind of, as we go, I'll give you that equation. 3 out of the 4 have their own special equation. The other, I'm sorry, 3 out of 7. The other 4 out of 7, the only way we could calculate those is using Newton's second law. Any of these forces can be solved for, given the right information, using Newton's second law. These 3 that I highlighted have their own special formulas that as we get to them, I'll kind of teach you that formula as we go. So Newton's laws of motion, since we're talking about Newton, everything is labeled after him. We should talk about Newton because he's kind of what a lot of this unit revolves around. So Sir Isaac Newton, 1600s, I think it was, 1600s. I think he moved it. 1643 he was born. He was a scientist and mathematician. He was going to school, I think it was during the time of the Black Plague, where they shut down the universities. And he was doing some stuff at home, trying to figure out some calculations, and the math didn't work. There was no math system in place. for him to do his calculations, so he had to create a new form of math called calculus to do the problems he wanted. Him and another guy is also credited with inventing calculus independently of each other, like the same kind of time frame. But Newton also came up with 3 laws of motion, also Newton's universal law of gravitation, which allows us to calculate the force of gravity anywhere in the universe. So we can determine what the weight of an object would be on Mars if we knew the right information. 3 laws of motion, we don't deal a whole lot with them in terms of, like, what are they? We use number 2 a lot for our calculations, but we should know at least what they are. Newton's laws of motion. The first one, an object at rest remains at rest unless acted upon by a net external force. There's a slash there because it could also read, a body in motion remains in motion unless acted upon by a net external force. Sometimes instead of saying a net external force, they'll say an unbalanced force. An object in motion tends to stay in motion unless acted upon by an unbalanced force. They sometimes use those terms as well. But they're interchangeable. It's also referred to as the law of motion, of inertia. And inertia is a term that means like resistance to change. Inertia is often associated with mass, not directly, but the more massive an object is, the harder it is for it to change, right? So think about like a semi at a stop sign. It takes a lot of engine, a big, strong engine, to get that semi moving and up to speed. It's resistant to change. Same thing is true if it's in motion. It takes a lot of strong braking system to stop it. Okay, so an object in motion, like this bowling ball, once it starts going, it's going to keep going on forever unless it's acted upon by a net external force like that, which causes it to stop and change direction. Now, it was slowing down a little bit, right? Okay, this isn't really going to roll on forever because of friction. Because there's some friction, and why? Because gravity's pulling it down on the floor, and because the gravity's pulling it on the floor, it's causing it to rub against the floor. Therefore, there's friction. But friction is a net external force, is the net external force that would cause that thing to slow down eventually, and not go on and on and on forever. Newton's second law. This is the one we do the most with. Newton's second law says sigma F. I believe it's the uppercase sigma, which in math means sum of, the summation. Right, that's what sigma means. So Newton's second law is often written as F net is equal to m times a. But F net means the sum of your forces, or the sum of the forces, you should probably really read. So I put sigma F, sum up your forces, add your forces, which is equal to F net, which is equal to mass times acceleration, ma. That's Newton's second law. Okay, so Newton's second law, sum of all my forces is equal to F net, which is equal to mass times acceleration. So when we talk about net external force, we're talking about F net. And we're saying, are my forces balanced or unbalanced? In order to find F net, we take the mass measured in kilograms, and we multiply by the acceleration, which is measured in meters per second squared, and we can determine an F net. Now, if your acceleration is 0 times whatever the mass is, means your F net is going to be 0. Or if your acceleration is not equal to 0, then that means your F net is not equal to 0, right? Because if any object has mass, so if it has some number that's not 0, it could be 1, it could be 1,000. But you take two non-zero numbers and you multiply them together and you get another non-zero number. So it has some value. Now, F net means overall, big picture, both directions, the x and the y. But when we go through and we sum up my forces, we only sum up our forces in the x direction, and then we only sum up our forces in the y direction. We keep our x's separate from our y's, just like we did in our 2D motion problems. We keep our x stuff separate from your y's. Now, F net really means like what happens when we put them back together. And since we don't deal with trig functions, we're either going to have an F net in the x, or the y, or neither. Okay, so it's either going to have an unbalanced force this way, an unbalanced force this direction, or none at all. But in reality, that's not the case. We could have an unbalanced force in the x and an unbalanced force in the y, which then means, like when we sum them all up, which means then we're going to have some unbalanced force that when we put them together would go off. But due to trig functions, we don't do problems like that. So what does it mean to sum up all my forces? So when we sum up all of our forces, we're going to do it in both the x and the y directions separately. And we're going to draw these things called free body diagrams. And the free body diagrams are really nothing more than boxes that have arrows coming out of it. And that's where I'm saying we don't do positives and negatives. We draw arrows to represent those. And in the x direction, you add your rights and you subtract your lefts, is what that will say eventually. You add your rights and you subtract your lefts. All right, so we add our rights and we subtract our lefts. And I'll show you what this means later in the class period. So we add any forces that are physically have an arrow pointing to the right, we subtract any values that are going left, and that will give us an F net. In the y direction, it's similar, except for we add our ups and we subtract our downs. You can say, well, aren't you really just adding your positive values and you're subtracting your negatives? And the answer is yeah, absolutely. But all of our numbers in our free body diagrams are going to be positive numbers. And we assign the directions with arrows, and we add and subtract accordingly, whether they're ups or downs, whether they're rights or they're lefts. So there's a string of statements that if one of these statements is true, all of the statements in this line are true. And I'd like you to add one to it that I forgot to do when I was typing this up. It says on the left-hand side, it says F net is equal to 0. And if F net is equal to 0, then, that's what the arrow would represent, then my acceleration is 0 meters per second squared. And that goes back to Newton's second law. If m times a, and a is 0, then that means my F net is 0. Or my F net is 0, then my a must also be 0. So my F net is equal to 0, that means my a is equal to 0 meters per second squared, because it's an acceleration. And an acceleration of 0 means that my velocity is constant. Constant velocity, acceleration is 0. That's motion. The thing I'd also like you to add, again, double-headed arrows, is that means my forces are balanced. If one of these statements is true in this line, every statement in this line is true. So if a problem says something like an object is moving with a constant velocity, oh, constant velocity, that means my F net is 0, which means my forces are balanced, which means my acceleration is 0. The object's acceleration is 0. Oh, that means balanced forces, velocity is constant, so F net is equal to 0. F net is 0, oh, hey, all those other statements are true. If one statement is true, all those statements are true. We call that, it's called an equilibrium problem. If my F net, this means does not equal 0. I hope you write an equal sign with a slash. You have to also add that, create that for your next part. So if your F net does not equal 0, some non-zero number, 1, 2, 10, 1,000, any number besides 0. So if F net does not equal 0, that means your acceleration is not equal to 0. You got to add not equal. You got to put that slash through it. Does not equal 0. If your acceleration doesn't equal 0, that means your velocity is changing. It is accelerating. Which then means my forces are unbalanced. In my F net, if my forces are unbalanced, if my forces are unbalanced to the right, that means my object is accelerating to the right, and my object is accelerating to the right, that means my net is to the right. They always go in the same direction. Third law, for every action, there is an equal and opposite reaction. We don't do a whole lot with Newton's third law. There's a couple physics teachers that I know that think Newton's third law is super, super, super important, and it is important, but they spend a lot of time talking about action-reaction pairs. If I take a baseball bat, and if I hit the baseball with 10 newtons worth of force, the baseball pushes back equally at 10 newtons worth of force. And you get really mad at me someday, you decide to punch me in the face. Sorry I made you mad that you had to punch me in the face. The good thing is, well, my hope is that your fist hurts in the process because of Newton's third law. You just punch me in the face, so my face pushed right back on your fist, and hopefully you're like, oh, his head is really hard. That's my hope. I don't know. So, but that's the every action equal opposite. So if you punch me in the face with 15 newtons worth of force, my face, even though it doesn't really, like I'm on the floor like, oh, like that, and you're like, yeah, take that, Mr. Davies. My face also pushed back at you with negative 15. That's Newton's third law. Sometimes people talk about it like in terms of like social things, like, oh, like, Johnny, why did you hit Billy? Well, Billy hit me first. Oh, well, that's okay then. Every action equal opposite reaction. He hit you, you hit him back. It's all okay. No, it's not really how that works, right? But Newton's law doesn't really apply to playground behaviors, but force of gravity. I want to talk about force of gravity because force of gravity is the most common force we use because any object that has mass and is in a gravitational field has a force of gravity. So, like, everything has a force of gravity. Especially because we're always talking about Earth, unless very specifically told otherwise. Everything that takes up space, volume, is made up of matter, has mass. So everything is mass, and if you're on Earth, then it's always going to have a force of gravity. The formula for force of gravity, F of G, is equal to m times g, where m is the variable that we use for mass. The unit we need to have it in order to do our calculation is in kilograms. If you were to use a balance setting on a lab table, that's in grams. You'd have to convert it to kilograms before you do your calculation. 1,000 grams per kilogram. By definition, mass is the amount of matter an object has. And I'm going to give you an example, and it's not a perfect example, but I like to think of it this way because I think it helps. If I were to say, does this tape dispenser have mass? Yeah, right? Because it's made up of matter, right? It's made up of matter. Does this object have some weight to it? Yeah. Yes. Now, weight and mass are two different things. Mass is based upon the amount of stuff this is made out of. Not perfect, but I'm going to say the amount of atoms this thing has. So if this thing had, I'm going to make up a random number that is not even close to them. If this thing had 1,000 atoms, not even close, 1,000 atoms, that 1,000 atoms is similar to the matter. It's made up of a certain amount of atoms. If I were to take this tape dispenser on my trip to the International Space Station, would it still have did I say 100 or 1,000 atoms? Does it still have 1,000 atoms in it if it's floating in space? Yeah, it does, right? It's still made up of matter. It still is made up of atoms. So does the amount of mass this object have here in my classroom versus on the International Space Station change? And the answer is no, because it still has the same amount of matter, it has the same amount of atoms. Now, atoms and matter aren't directly connected, but it's the general idea. So even if this is floating in space, it still has the same amount of atoms, it has the same amount of matter, so therefore we can say it's independent of the location. Now, when I'm talking location, I'm talking like Earth versus space. I'm talking Earth versus the moon. I'm talking Earth versus like Mars. I'm not saying like Weston, Wisconsin versus like Rhinelander, Wisconsin, or Miami Beach. Okay, I'm not talking that location, I'm talking like planetary stuff. So when we calculate force of gravity, it's mass times gravitational. This is independent of location, so therefore this tape dispenser is going to have the same amount of mass no matter where we go. However, it's going to have a different weight, a different F of G, because my gravitational acceleration is dependent of the location. My gravitational acceleration does change when I go to a different planet, when I go to the moon. So gravitational acceleration is a unit of meters per second squared. It is dependent of the location, and because we are going to spend most of our life, well, I shouldn't say that. I would assume you and I are going to spend most of our lives on Earth. I could be wrong. We tend to only worry about, we mostly worry about the gravitational acceleration here on Earth. And the gravitational acceleration here on Earth is 9.8. Notice how it does not say negative 9.8. It says 9.8. G is a scalar number, which means it's a number and a number only with no direction. Whenever I did a 2D motion problem, or I did a 1D motion in the y direction, and we said, hey, what's the force of gravity? Oh, gravity's the only force acting. And what's the acceleration? Oh, it's negative G. It's negative 9.8. G is 9.8. We had to assign it the direction, and the way we assigned it the direction was we gave it that negative sign. Any questions on that stuff? All right, let's flip it over then. So this is a free body diagram. A free body diagram is nothing more than a picture that has forces with arrows coming out of the box and has numbers next to it. The arrows should be roughly scaled. They don't have to be perfectly scaled, but if one force is bigger than the other, it should have a longer arrow than the other. And we title them by name. Now I borrowed this off the internet. As you can see, the source is cited right there. So their terms are a little bit different. Like they call it F grav, where I just call it F of G. They call it F norm, I just call it F of N. F of friction, F of frict, and I just say F of F. Okay, so the terms are slightly different, but the ideas are still there. But it's a box. I'm not a great artist, I don't know if you've noticed that yet, but I'm okay at drawing boxes. I'm okay. So we draw a box and we draw arrows and we label all of the forces acting on the object. A free body diagram is a picture with all the forces acting on it. So here's 4 free body diagrams. Now it says, the directions say, here's a free body diagram. For each situation, determine the F net acting upon the object. Now, F net is a calculation. We're going to use Newton's second law, and we're going to use it a couple times. But basically what it's asking is, are my forces balanced or unbalanced? If they're unbalanced, which one's bigger? Is it up, is it down? Is it my right, is it left? And how much bigger is it? That's really all F net is. I'll show you the full-on blown-out calculations just to show you step by step by step, and we will use that step by step by step later. But for right now, we're really just looking big picture. We only look at the x direction, then we only look at the y direction, and we look at them separately. But it all goes back to this string of sentences of right here, like, hey, if my F net is 0, then that means my acceleration is 0, my velocity is constant, my forces are balanced. Or if we say my F net is not 0, it has some number besides that, that means it's accelerating, it means my velocity is changing, and my forces are on balance. So let's take a look at this. If we take a look at situation 1, again, this is the full-on Newton's second law. We go through and we say, hey, let's sum up all my forces in the x direction, and that's going to equal F net in the x direction, which is equal to mass times acceleration in the x direction. Now, what this is asking, it's not asking me about acceleration. I don't really care about acceleration. So there's three parts to this. If we just kind of generically said this is part A, this is part B, and part C. We can say that A is equal to B. We can say that B is equal to C. And because A is equal to B and B is equal to C, we could also say that A is equal to C as well. But for this, we don't really need that last part. We're trying to determine what the F net is, and the way we do that is we sum up my forces in the x direction. Now, in the x direction, when we sum up all the forces, we add our rights, we subtract our lefts. So by building out our equation, in the x direction, I add my rights. So by name, I'm going to add my applied force. I'm going to subtract my lefts. So I'm going to subtract force of friction, and that's equal to F net in the x direction. Then we can go through and we can add values, and we can say add 5 minus 5 is equal to F net in the x direction. My F net in the x direction is equal to 0 newtons. So what's my net force in the x direction? 0. What does that mean? It means my forces are balanced. It's not accelerating in the x direction. My velocity is constant in the x direction. Then we do the exact same thing. The sum of all my forces in the y direction is equal to F net in the y direction, which is equal to mass times acceleration in the y direction. Now in the y direction, we add our ups and we subtract the downs. So we add all of the forces that are going up, and that would be my normal force. I subtract all of my forces going down, that's my F of G. Yeah, and I don't really care about the mass times acceleration because what I'm trying to determine is what is my F net in the y direction. My normal force has a value of 3, so I got to add the 3. My gravitational force has a value of 3, so I'm going to subtract that 3, which means my F net is equal to y, which is equal to F net in the y direction, which has a value of 0 newtons. And you say, well, I could have told you that a long time. Yes, I know. The intent is, this is the process. But really what we're asking, are they balanced or unbalanced? Are they balanced in the x direction? And the answer is, yeah, they're balanced in the x direction. So my F net in the x direction is 0. Are my forces balanced in the y direction? Yeah, so therefore my F net in the y direction is equal to 0. Let's take a look at letter B. Are my forces in the x direction and only the x direction, are they balanced or unbalanced? In the x direction. I'm sorry, I said x, I meant y. Let's start with the y, because I meant y. Are my forces in the y direction balanced or unbalanced? They're balanced. So because they're balanced, my net force in the y direction is 0, right? Because if my forces are balanced, my ups are equal to my downs, my F net is equal to 0. In the x direction, now this is the one I asked before, sorry, are my forces balanced or unbalanced? Which direction are they bigger, left or to the right?
Left.
How much bigger are they to the left?
5 newtons.
So then my F net is 5 newtons to the left. That's really all that calculation that I did in part 1, or part A did, is which one's bigger, my ups or my downs, which one's bigger, my rights or my lefts, and how much bigger are they. And the direction, we can say, is the left. Now, if we would have done, we add our rights, in the x direction, we add our rights, we subtract our lefts, we would then say my F net in the x direction was negative 5. That negative is the direction. Negative tells me that it's moving to the left. That's the idea. In the situation C, are we balanced or unbalanced? Balanced or unbalanced, the letter C?
Balanced.
So therefore F net is 0 or not 0? 0. What about in situation D? Balanced or unbalanced?
Not
which direction is bigger, up or down?
Up.
So my F net is gonna be up, is up. How much bigger is my up than my down? $15 newtons. Right? My up is 15 newtons bigger than my down, which means my acceleration is gonna be up. I don't know the number right now, but my acceleration will be up because my F net is up. Down here, it's kind of switching it. Now we're saying, what's my F? It's giving us the F net, we have to figure out the other. So my F net is 0, which, just to remind you, if my F net is 0, that means my acceleration is 0, which means my velocity is constant, and it means that all my forces are balanced in both the x and the y direction. So if my F net is 0, and if my right is 50, that means my left must be 50. So A is equal to 50. If my up is blank and my down is 200, add my up, subtract my downs, that must mean B is equal to 200. Oops, you can't see that. My ups minus my downs had to equal 0. My rights minus my left had to equal 0. Now this has an F net of 900 up. Are my forces balanced or unbalanced? Right, and the way we know that is because it says my F net is not 0. It's 900, which is not 0, which means then my forces are unbalanced. So they're unbalanced. Which one's bigger, my up or my down? My up is bigger. How much bigger is my up? So that must mean that C is 1100, right? Because it's 900 bigger than my down. So 1100 minus 200 has to equal 900 up. If it's 60 newtons to the left, which is bigger, my left or my right? How much bigger?
80.
How much bigger? 60. So my left is 80, that must mean my right is 20. Add my rights, subtract my lefts, 20 minus 60. Add my rights, subtract my lefts, is equal to negative 60. That negative is the left. Okay, so this is 60 bigger than this one. What's E have to equal then? 300, because in the y direction my forces are going to be balanced. If my net force is 30 newtons to the right, what's G equal? 50. What's F? Equal to H. That's a good answer. Okay? They're equal to each other. Now we could make up a number if we wanted to. We could call it 200, 200. We could call it 10. We could call it 10. It doesn't really matter, but they're equal to one another. All right. I have another sheet that I can't find. It was on here, and I moved it. Where did I put those? They were here. Oh, here they are. Okay. So, your homework sheet called Free Body Diagrams 2. Grab one there from the stool or the chair, or they're linked as a PDF via Canvas. We're going to go through a few of these. Okay, we're going to get you going on these called Free Body Diagrams 2. Free Body Diagrams 2 is similar to Free Body Diagrams 1, but now it's giving you information, and based on the information, we draw the picture. This introduction to forces, you might want to keep handy, because like this string of sentences is gonna be kinda helpful. There's no numbers associated with any of these. It's really just pictures. So if we have a book, again, I'm okay at drawing boxes. We have a book that's at rest on a tabletop. So there's my book on my table. Not too bad. Practiced already today. Now, a free body diagram is a picture that has all forces showing. So what forces are acting on this object? Now, anytime I say what forces are acting on the object, we're on Earth, and there's a gravitational field, and anything that takes up space is made of matter, has mass, so everything has mass. That means there's going to be a force of gravity. So whenever I say, hey, what force is acting on the object? If you say force of gravity, 99.9% of the time you will be correct. So what forces are acting on this thing?
Gravity.
Hey, gravity. And gravity always pulls straight towards the center of the Earth. Okay, so we have a force of gravity pointing down. Now, it's sitting at rest on the table. So what does that tell me about the velocity? Is it constant or changing?
Constant.
Which means my acceleration is 0 or not 0.
0.
Which means my F net is 0 or not 0.
0.
And my forces are balanced or unbalanced? Balanced. Are my forces balanced or unbalanced right now?
They're pretty balanced. Wait, not balanced.
They are not balanced right now, okay? So we're missing something. Now, normal force occurs when an object is sitting on a surface. So because it's sitting on a surface, there's a normal force. Now, because we said my F net is equal to 0, that means my forces should be balanced. We want to draw my normal force with about the same length as my gravitation. Doesn't have to be perfect. It should be close. It shouldn't be crazy different. And that's it. That's all we got to do for that free body diagram. If we take a look at number 3, it says an egg is free falling from the nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it is falling. Now I am going to get a little bit artistic here. Drew an egg instead of a box. Tried, went out of my comfort zone a little bit. And we have an egg that's free falling. What does free falling mean? What's the acceleration of that egg?
Negative G.
Negative 9.8 meters per second, right? So what forces are acting on this egg?
Gravity.
Okay, there's gravity. Anything else? And some of you might be saying air resistance, but it does say neglect air resistance. So that's it. That's the only force acting on an object in free fall. So we could say my F net, or my force is balanced or unbalanced. Unbalanced, and if we wanted to, so then we'd say F net is equal to 0 or not 0.
Not
And which direction is it unbalanced?
down.
Yeah, it's unbalanced down. So we can say my F net is down. And that's good enough for what we're doing. Let's try number 5. A rightward force is applied to a book. What's the opposite of a rightward force? A leftward force, right. So we have a book that's on a desk. There's my book on my desk. A rightward force is applied, so a rightward force is applied, which means that there is some type of an applied force. A rightward force is applied to a book in order to move it across the desk with a rightward acceleration. So does that mean acceleration is 0 or not 0? Not 0. And if my acceleration is to the right, that means my F net is also going to be to the right, which means my unbalanced forces are to the right. Consider frictional forces, neglect air resistance, diagram the forces acting on the book. So we have a rightward applied force. What are we missing here? Which direction does friction go?
The left, or the opposite
Right, it always opposes, so it's gonna go in the opposite direction. And which one's bigger, my right or my left? My right. So I'm gonna draw my left smaller than my right. Okay, so I just tried to draw that arrow shorter than that arrow. Doesn't have to be crazy, just visually it should be short. Are there any other forces acting on this thing?
Like gravity.
Yep, there's a force of gravity. Are there any other forces acting on this thing? I think I heard it. Yeah, there's a normal force because it's sliding across a desk or it's sitting on a desk. So we do have a normal force. Now what should be true about my normal force and my gravitational force arrow? It should be about the same because it is accelerating. Is it accelerating off the table?
No.
Is it accelerating through the table?
No.
So in the y direction, my forces should be balanced. Let's do number 4 quick. A flying squirrel is gliding from a tree to the ground at a constant velocity. So there's my flying squirrel. What forces are acting on it? A flying squirrel is gliding from the tree at a constant velocity. What does that mean about if my velocity is constant? Means, right, this whole line. You're right, it doesn't mean quite a few. It means my forces are balanced, which means my acceleration is 0, which means my net force is 0. So because of this, this tells me my acceleration is 0, which means my F net also is going to be 0, which means my forces have to be balanced. So what forces are acting on this squirrel?
Gravity.
Gravity. That's unbalanced, so it must have something going up. Nope, it's not sitting on a surface, so no normal force. Yeah, this one says consider air resistance. So we have an F of air, and that arrow should be about the same length as that arrow. And then that's the idea. You have 7 more. That's your homework for tomorrow's virtual day, is to draw these images, take a picture, upload it. It is available as PDF. If you so choose to do it that way, if you have any questions on these free body diagrams, take a quick picture, send me an email. I can mark it up and I can help you figure these out before you get back to school on Wednesday or Thursday. So if you have any questions, please let me know. Have a great day, everyone.